we're going to be looking at today is science literacy, and you'll notice that I'm talking about literacy versus literacy. So I talk about this in terms of a big L literacy and a small L literacy, and what's the difference, because that's really important that I've discovered within the science realm. So we're going to be going through this, and I'm hoping that by the end of this you'll see kind of the difference, but how the two actually work together. So when people, especially teachers, hear the word literacy, certain things come to mind. And it also is dependent upon the environment in which they're living. So in the education realm, when you hear the word literacy, the first thing that generally comes to mind is reading. And when you're in the science realm and you hear literacy, something else comes to mind, and it is not reading necessarily. So really, what is the difference? So we're going to start with literacy can be one of two things. It could be being literate in a given area, which is what I would call the big L literacy. Or literacy could also mean using literacy-specific abilities to make sense of information from a given area. And that's what I call the small L literacy. So as we go through this, I'm going to try and clarify both of those things. So just remember, we have the big L is being literate in a given area, and then the small L is using literacy-specific abilities. So what is scientific literacy? That is the big L literacy. According to James Trefil, scientific literacy is that matrix of knowledge that is needed to understand enough about the physical universe to deal with issues that come across our horizon in the news or elsewhere. So really what we're talking about here is content literacy. That is your knowledge about your physical sciences, earth sciences, life sciences, and the space sciences. So having that basic knowledge of understanding would be the big L literacy, the content literacy, being scientifically literate. But when we think about content literacy, then we're going to kind of slowly go into that small L literacy. According to Swafford and Kalis, content literacy is exemplified by individuals who use their background knowledge, they use print and non-print text, they use developing technologies, and they use the tools of reading, writing, speaking, listening, representing, viewing, and other signs and systems to explore, construct, learn, communicate information within a variety of social, cultural contexts, both in and out of school. So that last one, number 4, is probably the one as an educator you're most familiar with. That is, I'm going to be using these tools to really put out and communicate my understanding about some idea. So what is that small L literacy? That small L literacy is the ability to make meaning conjointly with verbal concepts, mathematical relationships, visual representations, and manual technical operations. This is according to Lemke. So really it goes back to that number 4 that we had on this previous slide. It's taking those tools together to construct meaning and communicate that meaning. That would be that small L literacy. So what are the science literacy skills? We're talking about things like to use a process to answer a question or a problem, to interpret data and draw conclusions, to understand the bigger picture, to determine relative importance of information, to communicate our findings, and to understand visual representations. So really what we're doing is we're taking information and we're trying to make sense of that information. Excuse me. And each one of those is actually very specific way of looking at science ideas and concepts. But we have a problem. We have a problem with science text. We all know, all of us, whether we're teaching science or we've gone through a science class, through school, college, what have you, that science text can be very challenging. And here are some of those challenges. the words are used in specialized ways. In other words, we have that specific terminology. Some of you who are knowledgeable about reading, we're talking about Tier 2, Tier 3 vocabulary. I personally like to use the word terminology because I'm a scientist and that's the way that we talk. The ideas and concepts are densely packed. In other words, there's a lot of information in a very short amount of space, and that can be challenging for students. The ideas are represented through multiple means: graphs, charts, pictures, text. As we think about text, all those are text by definition, but when we think about a science text or a textbook, even papers, it's not just a matter of having information in those other means, but they actually go back and forth. So you're not just looking at a graph and then you know everything, or you look at a picture and you know everything, but you move back and forth between the text and the image, back and forth, to get a bigger picture and understanding of what the author is trying to communicate. And then we also have that discipline-specific expertise that is assumed. That's that big L literacy. So there are some components that are maintained within or assumed by the writers that are trying to communicate information. So in the sciences, we have the three dimensions. We have the disciplinary core ideas, we have the science and engineering practices, and we have the cross-cutting concepts. The disciplinary core ideas would be that big L literacy that we talked about earlier. That is your earth, space, physical, and life sciences. Now we need to, how do the other two dimensions really work? And in my mind, those other two dimensions are those small L literacies. So in the science and engineering practices, these are the practices that scientists use to investigate, to model, develop theories about the natural world. And they're also practices that engineers use to design and build natural systems. So why do we use the term practice? Because in the past we've used the word inquiry, and some people may say these are literacy skills, but they're not really skills. We call them practices because they emphasize the engagement of investigation that requires not just the skill itself, but the knowledge that is specific to each of those practices. So the 8 practices that we have are listed here. So if I go back to that component of the specific knowledge of each practice, and I take, for example, analyzing and interpreting data, a lot of people like to use that one anytime they see a graph or a chart. Those are real. The analyzing and interpreting data really means analyzing means I'm going to take a big data set and I have to put it in some kind of a form that is usable. I have to organize it in some way, and then I'm able to make sense of it, which is the interpreting. So a lot of people, the general public, will say analyzing, interpreting data means looking at some kind of data set and making sense of it or figuring out what it means. That's just the interpretation part. The analyzing part is organizing it in some way, shape, or form. That's what we mean by the knowledge that is specific to each practice. Another dimension is your cross-cutting concepts. And the cross-cutting concepts are that lens through which sense-making around a phenomenon or a scenario occurs. And it helps to connect those disciplinary core ideas across disciplines and across grade bands. For those of you who are old like I am, I look at the cross-cutting concepts as what were commonly known as the academic expectations, if you remember those. These are very, very similar. So our cross-cutting concepts are these 7. They are just very, very generalized, but they help us make sense of new information. So for example, if I understand system and system models, if I understand what it means to have a system, if I understand how modeling helps me determine the interactions within that system, then I can use that cross-cutting concept no matter if I'm talking about something that's in the life sciences or something that's in the physical sciences. If I'm looking at an ecosystem, which is the most common, most people are aware of and understand, I use that idea, then I can utilize that similar idea to understand a system that might be in mechanics. So how do these really connect? How does that big L literacy and that small L literacy actually connect? In Benchmarks Project 2061, which was published many years ago, our goal for 2061 in science is that science literacy enhances the ability of a person to observe events perceptively, reflect on them thoughtfully, and comprehend explanations offered for them. In addition, those internal perceptions and reflections can provide a person with a basis for making decisions and taking action. So in other words, I can use my literacy practices, if you want to call them that, my skills, whatever terminology you want to use, my small L ability of literacy, in conjunction with my understanding of the content, my large L literacy, my science literacy, in order to make sense of the world, to make decisions, and then I can take actions upon those decisions. But there is a disconnect. In an article written by Robert Yeager, he says that literacy scholars are content to suggest that teaching science means helping all children to read technical science materials, including your text, tables, figures, and graphs, as if these artifacts represent science itself, and as if not focusing on such details results in a lack of scientific literacy. So the disconnect is that it's either one or the other. It's either I have to be able to do these things, my small L literacy, I can take a text, teach a kid how to read it and what it actually means, and then therefore I'm doing science and students are scientifically literate. And that's not the whole picture. It's a combination of the two. Yes, students need to be able to interpret that text in some way, shape, or form, but they also have to use their background knowledge, their understanding of the sciences themselves together. And that is what produces students who are scientifically literate. So what we have here are a couple of videos that will provide you an opportunity to see literacy in science. You've been provided a graphic organizer that will help you to, number one, identify which science and engineering practices and cross-cutting concepts are most prevalent in the lessons that you see. And number two, what evidence you have to support your findings or what you think. So it's not so much that there's a right or wrong answer. This is an opportunity for you to see how the small L literacy components of science actually are supporting the big L literacy of science. That is, these students are becoming more scientifically literate. In the first video around ecosystems and how ecosystems interact. So if you'll take some time, this first video is about 11 minutes long, watch the video, and then after the video, pause and have a discussion with your colleagues about what you have found, what you've discovered, what you see, and possibly what would be the next steps of thinking about your own practice of what's going on within your classrooms or within your department. So now you've had the opportunity to see one video, and I'm hoping that you saw some things that are very different, but also some things that you are actually doing yourself. The second video, very similarly, you have the graphic organizer, but this time, this particular lesson is in regards to an engineering classroom, an engineering lesson, just to let you see what the similarities and differences are. This video is a little bit shorter, it's about 6 minutes long, but again, I hope you have that opportunity to really see what the teacher's doing, what the students are doing, which is also very important. And then afterwards, pause and have that similar discussion with your colleagues to see what kinds of things you observed, and again, reflecting on your own personal practice within your classroom or within your department. So I hope that you and your colleagues had some very good productive discussions after both of these videos as to what you've observed. We'll be providing you a copy of my notes of what I saw But just realize that just because I wrote it down doesn't mean it's the quote-unquote correct answer, because everybody will see something different. You may have seen something that I didn't see, and you're perfectly valid. But I'm just giving you another example of somebody else's ideas. So as we close up for today, and I'm hoping that this has been informative and useful for you, here's some things for you to think about. And what I'm going to share with you are my own learnings and thought processes as I've studied this idea of science literacy, being scientifically literate for a number of years. First of all, science educators use discipline-specific literacy practices naturally. We do it every single day, but no one taught us. We learned how to do it on our own. But what we need to do is become cognizant of how we ourselves use those practices. And once we become cognizant of it, then we can make it visible to our students so that the students can be able to use those same practices. So in other words, we need to be more intentional in helping students build these skills. So as we are utilizing these practices, then we need to tell students what our thinking is. We need to make it visible, because the result then will be a science literate citizenry. And this is what we actually need. And this is the intent of science education.